Welcome to OPSWAT, and thank you for attending today's presentation. Today's topic is securing AVEVA Pi system databases using data diodes. We'll look at a number of areas in terms of securing Pi databases in terms of security, performance, scalability, and flexibility. My name is Mark Tusant. I'm a senior product manager at OPSWAT. I'm responsible for the MetaDefender Netwall line of data diodes and security gateways. I've been with OPSWAT for just over 2.5 years, but have been in the diode and network segmentation space for more than 7 years. So a little bit about OPSWAT. We protect the world's critical infrastructure with a range of product portfolio to secure all aspects of OT, whether it's moving data from OT to IT, whether it's moving data from the IT network into OT. And again, there's a broad portfolio of products to secure all aspects of critical infrastructure OT environments. So let's start off talking about why AVEVA Pi environments are critical. So AVEVA Pi systems, we see them all over the critical infrastructure industry. They're the industry standard for storing, aggregating, contextualizing, and using real-time operational data. They're considered, by their customers, the crown jewel, the historian of record data source. And very often when we at OPSWAT engage with customers, their largest concern and their primary use case is securing their AVEVA Pi database. This is mission critical, and any potential vulnerabilities or attack on the Pi database could have severe consequences for the operation. So let's talk a little bit about the nature of AVEVA Pi environments is that it's critical, and which also leads to Pi implementations to be attractive cybersecurity targets. The reality of it is that isolating or air gapping Pi infrastructure, it protects from external threats, but it's not practical. So why is that? Well, the business needs access to that mission critical operational data. So while air gapping networks is most secure, it's not practical from a business perspective. So this is where data diodes and security gateways come into play to secure these OT Pi infrastructures. Let's take a look at what we see as we engage with customers that are AVEVA Pi users. We notice some market trends that are, when you look to secure them, you need to keep in mind because things are evolving. And first and foremost, Pi databases are getting larger and larger. 3 years ago, a 50,000 tag database or a 75,000 tag database might be considered large. We're seeing now upwards of 150,000 tags, 200,000 tags. So Pi databases are getting larger. They're also getting more active, so they're generating more data more frequently. Pi architectures are getting more complex, and we'll talk a little bit about some of those architectures as we go on. We're seeing widespread use now of Pi collectives, where we have redundant Pi databases on the OT and the IT side. High availability has become critical, and we're seeing now customers looking to implement for their Pi infrastructures cross-geography high availability requirements, where you may have a requirement to fail over one data center to another without any data loss. And then customers are demanding that solutions that for replicating and securing AVEVA Pi provide for simultaneous transfer of the Pi archive data records, schema, and historical backfill. So these are some of the areas that when we look at our Pi customers, what they are faced with in terms of how they're evolving in the marketplace. So the security challenge that results from this is, how do you secure AVEVA Pi systems while ensuring that your data is accurately replicated and available to all key stakeholders on the IT or corporate side of your network? So to expound on that, when you talk about the security challenge, the underlying challenge is firewalls are just not good enough. By their nature, firewalls are bidirectional. They pass routable information between networks, so there is no network confidentiality between the OT and the IT network. Firewalls are software-based, so they require configuration. They're rules-based, which adds to the possibility of human error. Think about a firewall with 200 firewall rules. What's the likelihood that there's errors within those 200 firewall rules? What's the likelihood that data flows have been configured, but then are no longer used, leaving things like open ports exposed to the internet? So the firewall challenge is what our customers are faced with. And I mentioned before, a total air gap is just not practical. The business needs access to the real-time operational data. So we see organizations implementing data diodes in order to secure their AVEVA Pi environments. So what is a data diode, or as we call it, an optical diode? An optical diode has two sides. On the left-hand side here is the OT network, and on the right-hand side is the IT network. So fundamentally, diodes convert electrons to light, and we move it across an optical fiber. On the left-hand side, you've got we convert into light. You've got a photo transmitter on the left-hand side where it says processor. It can only transmit light across the optical fiber. On the right-hand side, you've got a photo receiver that can only receive data. So there is no back channel from the IT network to the OT network. We convert that protocol back into its native format and then route it onto its final destination. So the nature of a diode is that it works based on the laws of physics. It is physically impossible, because we're converting data into light and then back into data. There is no return path, and it cannot be hacked. And some of the benefits of diodes, and especially over firewalls, it's simple and easy to install and configure. In many respects with diodes, we set it and we forget it. There's not a need for frequent patching and things like that. Because we're optically enforce unidirectional data flow, no one can get from the IT network into the OT network. And data diodes nowadays offer a wide range of capacity, performance, and form factors. So who's using data diodes today? Data diodes are not new. They've been in existence for more than 20 years. They're widely used in oil and gas, power generation, transmission and distribution, and really across all 16 critical infrastructure verticals, things like manufacturing, water, wastewater, widespread across the critical infrastructure vertical markets. And some of the benefits, they're infinitely more secure than a firewall. They're very reliable with unsurpassed data delivery, and that protection that they provide isolates OT and ICS assets against cyber attacks. So what are the features of an optical diode that gives us this security profile as well as reliability? Well, they deploy one-way data flow. I talked about that data flow is hardware enforced, which means that it's governed by the laws of physics. We convert data into light and then back into data over the data diode. There is no return path. We utilize what's called a protocol break, which is a non-network connection between the source and destination. And I'll elaborate a little bit more on this in a subsequent slide. We deploy redundant optical connections to ensure that there's data integrity checks to achieve unsurpassed reliability, with advanced tuning for optimized data flow. And the optical diodes, today's topic is AVEVA Pi, but they support a range of industrial protocols as well as IT protocols and can run multiple simultaneous data flows across a single optical diode device. And finally, they're scalable. So depending on your needs, the amount of data you need to transfer from OT to IT, they're scalable. So with solutions running from 100 megabits per second to a gig to 10 gig options. So let's talk about the non-routable protocol break, which is essentially, I call the secret sauce of optical diodes. So what we do is we proxy an incoming communication from the source network. In this case, we have a TCP communication. We proxy that with TCP. The source network is looking for an acknowledgement. So that proxy receives the TCP session and provides the acknowledgement back to the source network. And then we, on the data diode, on the left-hand side, you see a blue server, which is the OT network. And on the right-hand side, you see a red server, which is the IT network. And what we do is we take that incoming TCP packet and we take all of the routable information in the data header, we strip it out and we discard it. We're left only with the data payload. We have a concept of a data channel. So as you configure the optical diode, you assign a particular data flow to a numbered channel. In this case, let's say that this communication is assigned to data channel 5. So we take that data payload, we convert it into light. And as I mentioned before, the blue side has an optical transmitter, but no receiver. The red side has an optical receiver, but no transmitter. So we move that data payload across the optical fiber. It's coming in on data channel 5. So the red server knows any data coming in on data channel 5 has to be routed to an assigned destination IP address. So we take that routing information and we reassemble that data payload into a TCP packet and we route it to its final destination. So as I mentioned before, there's total network confidentiality between the OT and IT networks. Because of the protocol break, because we convert data into light and back to data, neither of these networks know that the other one exists. There's complete network confidentiality. So this is an important concept to understand in understanding how data diodes work. Let's shift gears now and talk a little bit about some of the architectures that are supported using optical diodes. Probably the most basic is a one-to-one relationship where we're replicating a single AVEVA PI database on the OT network to an IT network, AVEVA PI database. We deploy a connector service in the OT network as well as on the IT network, and we move that data across the optical diode unidirectionally to that destination PI database. And this is a very common use case that we see out there. Also, we have use cases whereby we have a need for a many-to-one, where we may have multiple power generation plants, each with their own AVEVA PI database. We want to simultaneously replicate that data across the data diode and then aggregate it into a single AVEVA PI corporate database. We have PI collectives, I mentioned earlier, whereby customers are deploying redundant or maybe even triplicate AVEVA PI databases to provide redundancy on the OT network as well as on the IT network. So these are very common today that the solution needs to support PI collectives. High availability. There's a requirement more and more frequently for customers that need high availability redundant data diode environments. And we deploy multiple data streams, multiple sets of data diodes to provide that redundancy. And this is evolving into not only redundant pairs within a single site to now deploying redundant pairs in cross-geographic sites to provide that geographic failover in the event that, say, one data center goes down and then the other data center becomes live. So when you look at a data diode security solution for your AVEVA PI system, there's some things that need to be considered because not all solutions are the same. So there's a number of considerations to take into account to ensure that the solution that you select, is most suitable for your AVEVA PI environment. And first off is the replication method. AVEVA PI generally supports two methods for replicating data. One is a pi-to-pi replication, whereby tags, if you add new tags or delete tags, have to be added or deleted on both the OT network and on the IT network separately. And then there's pi database replication, where we replicate the database, but if tags are created on the OT side, they're automatically replicated from the OT network to the IT network. So it's important that the solution that you choose is capable of working with your pi replication methods, whether it be pi-to-pi or pi database replication. Next, it's important that your solution can automatically replicate tag changes on the OT network. As I mentioned, databases are getting larger, they're getting more active, so things are changing more frequently on the OT side of the pi database. So it's really important that you can replicate those changes, whether it's new tags, whether it's naming, whether it's attributes, automatically without needing to have manual intervention on the IT side. Does the solution scale? As I mentioned earlier, pi databases keep getting larger and larger, and most customers that we engage with their AVEVA Pi databases, looking at data diodes, come to us and say, I have 75,000 tags today, but I anticipate having 150 or 200,000 tags in the next year to two. So it's important that the solution that you select is capable of scaling. It's important that the solution also can map to the architecture of your AVEVA Pi systems, whether it's a one-to-one replication or a many-to-one. Does the solution support Pi collectives with automatically not interrupting the flow of data if a Pi collective fails over to another Pi database? Does that solution, is there any gap in data flow when that fails over? The best solutions do not have any gap in data loss when those Pi systems fail over. It's important that the solution can handle simultaneous transfer of Pi data archive records while simultaneously refreshing database schema and run historical backfill to backfill any historical gaps in data. So it's important that all three of these things can happen simultaneously without having to shut down the transfer of Pi data archive records while you complete historical backfill. It's important that all three of these things can happen simultaneously. Performance is also really important because AVEVA Pi offers three methods to replicate data or to integrate with the Pi database to replicate that data. The first is the Linux API, which has been around for a long time, but it's currently deprecated. And although some solutions still use it, it tends to be somewhat slow and limited and is not currently being updated by AVEVA Pi. There's also an option to use the PiWeb API, which in smaller databases works okay. As you get larger, there are a number of performance issues that the PiWeb API has. So if you're getting above 50,000 tags, you may run into some performance issues in terms of securing those databases over data diodes. We've selected a method using the AVEVA Pi Asset Framework SDK, which runs on the Pi server or on a separate flanking server. And what we found is we've gotten exponential performance improvements using the Asset Framework SDK. So it's important to understand, what methodology, the solution utilizes, because performance is important. As we move data to the cloud and we have more hops on the IT network side, the older frameworks or the older integration methodologies have a hard time keeping up and writing fast enough to the IT Pi server. And we found that the Asset Framework SDK markedly improves the performance of the replication. And then finally, high availability. It's important that your solution can support from the not only the Pi collective, but the optical diode high availability cell, so that you can ensure that you have redundancy not only in your Pi databases, but in the data diode that is sending the data from OT to IT. So these are some considerations to take when looking at the various solutions that are out there in the marketplace, because not all are equal, and you will find that some of the lessons learned that we've embedded into our product, take into consideration some of these areas that need to be optimized to ensure that you have the best replication solution possible. So what are the key takeaways? AVEVA Pi environments are become attractive cyber attack targets. Isolating or air gapping the Pi infrastructure on the OT networks works very well in protecting internal threats, but it's not practical because the business needs access to that mission critical Pi data. And data diodes are being deployed really across the spectrum of critical infrastructure verticals to secure those Pi environments. And as I mentioned, the use of data diodes in critical infrastructure to protect Pi environments is widespread. So thank you for your time today. As I mentioned before, if you have questions, please put them in the chat. And with that, we'll conclude our session today. Thanks again for your time.